Everyone, this is Manikanta from studying in BTech first year, IRE College. Today I'm going to discuss about Tech Talk topic on subject physics, and my topic is 3D nanocarbon interconnects. Carbon nanotubes discovery. In the late 1950s, Roger Bacon at Carbide found a strange new carbon fiber by studying carbon under conditions near its triple point. He observed straight, hollow tubes of carbon that appeared to consist in graphitic layers of carbon separated by the same spacing as the planar layers of graphite. In the 1970s, Morinobu Endo observed these tubes again, produced by the gas phase process. Indeed, he even observed some tubes consisting in only a single layer of rolled up graphite. And in 1991, after the discovery and verification of fullerenes, Somio Lijima of NEC observed multi-wall nanotubes formed in a carbon arc discharge. And 2 years later, he and Donald Bethune at IBM independently observed single-wall nanotubes, Buki tubes. Let us discuss about carbon nanotubes. Carbon nanotubes are tabular forms of carbon that can be envisaged as graphene sheets rolled into cylindrical form. These nanotubes have diameters of few nanometers and their lengths are up to several micrometers. Each nanotube is made up of a hexagonal network of covalently bonded carbon atoms. Carbon nanotubes are of two types, single-walled and multi-walled. A single-walled carbon nanotube (SWNT) consists of a single graphene cylinder, whereas a multi-walled carbon nanotube (MWNT) comprises of several concentric graphene cylinders. Depending on the way of rolling of graphite sheets, single-walled nanotubes are of different types. Viz armchair, zigzag, and chiral could be produced. They can be represented using the method given by Hamada. For example, to realize an n, m nanotube, one has to move n times a1 from the selected origin and then m times a2. On rolling the graphite sheet, these points coincide to form the n, m nanotube. Thus, armchair, zigzag, and chiral nanotubes can be represented as n, n, 0, and n, m respectively. Different wrapping results in different structures and electronic properties. Types of CNTs. Carbon nanotubes are of two types, single-wall carbon nanotube (SWNT), multi-wall carbon nanotube (MWNT). Single-wall nanotube. Single-wall nanotube consists of one cylinder. It is made of single graphene sheet rolled up into cylinder closed by two caps, semi-fullerenes. The SWNTs have diameter in range of 0.5 to 2 nanometer. The length is in the range of 50 to 150 micrometer length. The SWNTs are microporous and specific surface area is in a range of 1300 meter square by G outer surface. SWCNTs are commonly arranged in bundles. SWNTs have less topological defects and have better mechanical and electrophysical properties. Electronic properties of SWNTs are governed by two factors, tube diameters and helicity, which further depend on the way graphene layer is rolled up, armchair or chiral. Armchair SWNTs shows conductivity as similar to metal, whereas zigzag SWNTs behave as semiconductors. In catalysis, CNTs have high application as support. Electrical conductivity, surface, surface curvature, and presence of inner cavity in CNTs make the metal support interaction different, different compared to that, that in activated carbon or graphite support. Mechanically, bent SWNTs present kink sites that are chemically more active. Metal nanoparticles size depends strongly on metal CNT interactions with stronger interaction giving rise to smaller nanoparticles. Studies have shown that convex surface, convex surface of CNTs are more reactive than concave surface, and the difference is different in reactivity increases when the tube diameter decreases. Multi-wall nanotubes. Multi-wall nanotubes consist of many nested concentric SWNTs cylinders with increasing successive radii. The concentric walls are spaced regularly at 0.34 nanometer, similar to intergraphene distance. MWNTs have outer diameter in range of 2 to 100 nanometers. Depending on number of coaxial tubes present, MWNTs are usually mesoporous in nature and specific area depends on the number of walls. The length of MWNTs can range from few to 100 micrometers. The advantage of MWNT over SWNT is that the multi-shell structures of MWNT are stiffer than single wall, hence stability is higher. Also, large-scale synthesis of MWNT is possible by various methods. The most common characterization techniques of these materials are electron microscopy, Raman spectroscopy, TGA, IR, and UV vis. Physical properties of carbon nanotubes. Mechanical properties, thermal properties, electronic properties, magnetic properties, and semiconducting properties. But here we discuss about mechanical properties and thermal properties. Mechanical properties. The strength of the carbon-carbon bond gives rise to the extreme interest in the mechanical properties of nanotubes. Theoretically, they should be stiffer and stronger than any substance. Stimulations and experiments demonstrate a remarkable bend don't break response of individual SWNT to large transverse deformations. An example from Jacobson simulation is shown in figure. The two segments on either side of the buccal region can be bent into an acute angle without breaking bonds. Simulations and experiments show the full recovery of the straight perfect cube once the force is removed. Young's modulus of the cantilevered individual MWNT was measured as 1 to 1.8 TPa from the amplitude of thermally driven vibrations observed in the TEM. At the low end, this is only approx to 20% better than the best high modulus graphite fibers. Multi-wall nanotubes and SWNT bundles may be stiffer in bending but are expected to be weaker in tension due to pull-out of individual tubes. And there is the comparison of mechanical properties between single-wall and multi-wall nanotube as well as steel, epoxy, and wood. Thermal properties. All nanotubes are expected to be very good thermal conductors along with tube but good but good insulators laterally to the tube axis. It is predicted that carbon nanotubes will be able to transmit up to 6000 watts per meter per Kelvin at room temperature. Compare this to copper, a metal well known for its good thermal conductivity which transmits 385 watts per meter per Kelvin. The temperature stability of carbon nanotubes is estimated to be up to 2800 degrees Celsius in vacuum and about 750 degrees Celsius in air. Synthesis of CNTs. There are two main methods of preparation of CNT. Sublimation of graphite with subsequent desublimation, arc discharge method laser ablation, and second one is decomposition of carbon containing compounds, chemical vapor deposition. First one, Sublimation of graphite with subsequent desublimation. This method involves condensation of carbon atoms generated from the evaporation of solid carbon sources of graphite. The sublimation of a solid can be done using electric arc or laser ablation where the temperature reaches to 2500 to 3500 degrees Celsius. And this is the schematic diagram of CNT formation by sublimation of graphite about arc discharge as well as laser ablation. The electric arc discharge method is one of the efficient techniques for synthesis of CNT. Typically, about 60 to 70 watt percent of the arc synthesized soot is CNT, and the rest of the soot comprises of fullerenes, amorphous carbon, and catalyst nanoparticles. In electric arc discharge production of CNT, two graphite rods are used and a current is passed continuously between the electrodes. The anode is drilled and filled with catalysts. The metal oxides, nickel, copper, iron, are used as catalyst. In some cases, the catalyst or graphite composite is used as electrode. The synthesis is performed in cooled chamber a- in presence of helium, argon, or methane environment. During the arcing, the catalyst or graphene anode is evaporated and consumed with simultaneous carbon deposition around the cathode. The quality of CNT samples depends upon arc stability, current density, and cooling of cathode. In laser ablation method, the graphite target is subjected to laser and sublimated carbon is recollected. Inert gas atmosphere is maintained within the chamber. And the other applications are CNT is also being investigated as support for biocatalysts. CNTs have been used for enzyme immobilization, which increases enzyme stability, control of pore size, multiple active sites, and reduced mass transfer limitations. CNTs have also been used as direct catalyst for some specific reactions such as methanation to produce carbon oxide and carbon dioxide free hydrogen, oxidative dehydrogenation of ethyl benzene to styrene, and oxidative dehydrogenation of propane to propene, selective oxidation of H2S, oxidation of aniline, esterification, and hydroxylation. By this, I want to end the session. Thank you.